The last bit that you guys need to know about that I'm going to talk about today are CDs. And CDs, guys use all the time, I'm sure. How do they work? How do you use them to store information? And you can actually do calculations of how much information you can store on a CD. CDs, generally they have like a reflective part, some sort of aluminum, and some plastic that protects it. And on this aluminum, what is stored are actually what they call pits and land, but they're just bumps. They're bumps on the surface of the aluminum. And what that does is when you're reading it with a laser in a specific wavelength, and it's a red, I think the CD standard is some a red laser. They're sending a red laser up, and it bounces back. Now, if you're just sending it off of here, that's fine. If it reflects back, you're going to see a bright spot. And if you send a laser up here and it bounces back, you'll also see a bright spot. But what happens is, as the CD is spinning, you send up a laser part here, and some of it also gets here. Now then, when this guy reflects, very similar to what we've been talking about thin films, when this guy reflects, if these guys are not in phase, we can get some interference. And in fact, that's how they designed this, is that if this laser is, let's say, 600 nanometers, they make these pits to be 1/4 that distance. And so what that means is if you're at 1/4 the distance, you'll go in with like half of a wave, and then come back out with the other half of the wave. And basically interfere with yourself. So maybe if we have a peak here, so it goes down and then comes back as a trough, then you have the peak here coming in, then it's basically a destructive interference. So those things, the destructive interference is very easy to read because the laser reflecting back stops reflecting, it looks dark. And so what the CD reader sees is basically a series of light and dark flashes. And the dark flashes indicate that there are bits being transmitted. Usually the dark flashes, the pit to be 1/4 the wavelength in the plastic. And how much information can a CD hold? Well, the track spacing is about 1.6 microliters. Is 2 pi r, so that would be 2 times pi times 4 centimeters. So that should be somewhere around 25 centimeters. So that's how long an average track would be. And then we could say, well, how many tracks do we have on this CD? Well, if we're going from 2 centimeters up to 6 centimeters, then we're going over about 4 centimeters. And each track is separated by 1.6 micrometers, so 1.6 micrometers. And if you do the division, I think this works out to be something like 25,000. This is the number of tracks. So this works out to be about 25,000 tracks. And if we have 25,000 tracks, each of about 25 centimeters, how many bits can we put on one of these 25 centimeters tracks? And that would be the number of bits per track. It would be just 25 centimeters over 800 nanometers. And I'm not sure what that would be. A lot. 0.25 over 8 times 10 to the minus 7. Yes, that's like 7. So it looks like somewhere around 300,000 bits. I think it's probably more like 3 million. But then if you multiply by the number of tracks, you actually get that there's somewhere around 980 megabytes on one CD. And if you do this for DVDs, the track spacing is a little bit shorter, and the bit spacing is a little bit smaller, and so you can get with 4 gig. But that's how you do these types of calculations. They're pretty straightforward. How's that? Okay. I have a worksheet. Hold your thoughts a little. I have a worksheet that I'll give you to put online, and on Wednesday I'm going to talk about CCDs, charge coupled devices. How you get images.
Are you sure you don't mean like CCD, like this class?
I mean.